Hi everybody. In this video we are going to discuss APES Unit 7.3, so thermal inversion. We're going to describe what it is and how does it actually relate to the topic of atmospheric pollution, and if there's anything that we can do about it. Okay, so this is an idea that we've talked about before when we've talked about urbanization and also sustainability in terms of energy, because urban areas do have a tendency to be hotter, and there are, additional tactics that need to be put into place to mitigate that additional heat. And it's called the urban heat island effect. So this just is a graphic that highlights nicely the areas of, urbanization or downtown versus commercial, and kind of working our way out to rural areas. And the idea that the downtown areas just naturally have a higher temperature around them due to this heat island effect. And really, it's because, I think on the next slide I'll talk a little bit more about it, they don't have the reflective ability that the rural areas have in terms of UV radiation and sun exposure. The asphalt and the cement and the concrete buildings are, a sink for sucking up and absorbing that heat, and then it kind of traps that heat. So naturally, those areas tend to be warmer, whereas in the highly vegetative areas of the rural communities, that's not as much of an issue. So this kind of graphic just highlights the temperature differential, which can be, up to, 7 degrees difference just whether you're in a city or in the country. But there's really two major effects that are taking place here. There is lower albedo, which goes along with that reflectivity. Remember, albedo is the ability to reflect the sun's rays. If you have high albedo, you have high reflective surfaces. For example, a snow-covered area has high albedo, which is why it helps when it's cold keep everything colder, and why you're kind of blinded by the reflective sun rays when there is snow-covered land. But in city areas, you have low albedo, so the concrete surfaces are darker. Black absorbs. If you've ever worn a black t-shirt on a hot, sunny day, you get warmer faster because it absorbs those sun's rays, and therefore more energy ends up being given off as heat at the end versus what trees and other vegetation naturally absorb. So you are ending up with just more trapped heat. Also, evapotranspiration. So in this case, water that evaporates from surfaces and the transpiration of plants. If we think about, plants taking up water from the roots, and then they do end up giving off water in their own transpiration processes, it often cools the area. If we think about evaporation, when we sweat, that evaporation cools us down. Well, that evapotranspiration that occurs from vegetation carries the heat a little bit out of the surface and into the atmosphere. So it helps cool down those areas. And that's something that the city doesn't have. So again, the city ends up being 3 to 10 degrees hotter because of this heat island effect. And those are two of the main causes or drivers of that. Which also leads into this idea of thermal inversion, because we're talking about temperature, differentials. And the idea is that under normal circumstances, warm air rises. And the air currents or the air convection carries air pollutants, right? If the city is giving off air pollutants, typically what happens is it gets trapped in the air, and as the warm air rises, it carries those pollutants away from the surface and then spreads them out into the atmosphere, which sounds bad, but at least from a human health standpoint, you are kind of removing those pollutants from the surface and getting them up higher into the atmosphere so it can do you less damage. However, during something called thermal inversion, you don't get that natural gradient. So on the left, you see that the warm air is on the bottom, and then as you move up into the atmosphere, we've already learned it gets colder and colder and colder. But during this heat inversion process, it's flipped. What ends up happening is that a cooler mass or cold air ends up being trapped underneath a warm air pocket. And it can't escape. That cold air is kind of trapped below the warm air, and it won't work its way through the warm air. It just has to kind of stay there. And then it inverts the normal temperature gradient. You have colder air trapped underneath and warm air on top. So it does not allow for the carrying away of that air pollutants. If the smog, it just kind of circulates around instead of being up and carried away. And you might ask, all right, well, how does this happen? Well, sometimes a normal warm front might move in and just kind of trap some of the cold air. Typically the surface in, wide open on a clear night, the surfaces cool very quickly because the thermal transfer on a cool, clear night will radiate a lot of that heat out of the surface and cool down that surface temperature really quickly. And so that's really why if in the morning you see dew on the lawn or fog in the morning, it's a result of thermal inversion because it got colder underneath some warm air, and so that condensation kind of got trapped in the lower level, and then we can see that as fog or as dew on the grass in our yards. But on the pollutant side of things, the smog can oftentimes get trapped in there too. Hot urban surfaces, right? They've trapped in all of that heat during the day, and then they begin cooling overnight. So the urban surfaces have a tendency to kind of exacerbate the thermal inversion, especially in valleys. The warm air kind of comes in and caps everything off and really can trap in a lot of that cold air, especially in a valley where it's really hard to escape. So again, that's where places like California are particularly vulnerable as well if they are in a valley area. So because the cold air at the surface is trapped, like I had mentioned, convection doesn't carry away the pollutants. So anything like smog, particulate matter, ozone, SOx and NOx, they can't get away. And wind usually is what solves this whole problem, right? The wind kind of creates the gusts. It will carry away the pollutants. It will help mix the warm and cold air and kind of prevent the layers from happening. But as I mentioned, in those valley areas, winds are already limited, airflow is limited, so it just takes longer for these inversions to subside. And that's again another reason why we see the cloud of smoke kind of trapped in that lower level, because the warm air that's above in the atmosphere is kind of holding it down. Okay. So that's the idea of thermal inversion. It's just the normal switch from warm at the surface all the way up to colder and colder as you move up. That normal circumstance gets inverted. Some kind of warm air mass is trapping cold air underneath, whether it is because of the heat island effect or because a warm air front moves in. Again, it's a natural thing that also occurs. And it traps in that smog as a result. And then people will breathe this in and have consequences that occur. So let's try a couple of review questions. So go ahead and pause and give this one a try. And when you think you have it, go ahead and push play. Okay. So this, it shows you, is atmospheric layers in thermal inversion, and it asks you if it was relabeled to illustrate normal conditions. So normal conditions would have a gradient of warm towards the surface and then get cooler as you go up. So because of that, B is the best answer here. Okay, we have the same picture, but a new question, so go ahead and pause and give it a try, and when you're ready, hit play. All right. And so this one is a little tricky because a lot of these statements are accurate, but there's only really one that really explains why the pollutants would be concentrated closest to the Earth's surface. So of all of these true statements, right, like the layer that's second closest to the surface is less dense than the air above it, yes, the warm air is less dense than the cooler air. That's true. The inversion layer is warmer than the air layer that is farthest from the Earth's surface. Yep, that's a true statement. However, C is the best answer here because the reason why pollutants tend to concentrate on the layer closest is because that cool trapped air is denser than the warm air. So it just lingers, it hangs, it sinks right above the city. And the warm air helps to trap it in so it can't escape. The winds aren't coming through. The warm air acts as a cap, and the cool air just is, because it's dense, wants to sink back down, and that really solidifies the concentration of the pollutants in that air and not being able to escape. So that's why C is the best answer here. Okay, so here is the last. Go ahead and pause and give it a try. Okay, so this one is showing you a figure where it says different layers in an inversion. So you already know without anything, like it says in the picture, subtropical high pressure, and that can be a little confusing, but it tells you that it's already inverted. Which of the following shows the sequence of thermal layers moving vertically from the surface? So basically A to B to C, what would the temperature-ish be as we move up? And because of that, we would have in an inversion, cool, then warm, then cool. So you would look for the answer choice that has that, in this case, C. So in this picture, we have the cool sea breeze coming in. So that's what's actually cooling down the temperatures on the surface. And then we have warm and cool. That distribution is being caused by a high pressure area. But even if you didn't know that, you know that it's an inversion diagram, so that you know that that normal gradient of warm on the surface and colder as you move up is flip-flopped. So C is the best. All right, that wraps up thermal inversion. Thank you.